Hello.
Hello.
Yes, I mean, Anupam, can you hear us? Can you hear me?
Yes, I can. Yeah,
Hello.
I
Yeah,
can.
Pankaj, I met you a long time ago. Yeah,
Yes, indeed. It has been too long.
yeah, yeah. Okay, so I think we will just be starting. So let me introduce our speaker and say a few things. So it is a privilege to have Professor Anupam Garg from Northwestern University as a speaker to celebrate International Year of Quantum at our center, which is Center for Quantum Engineering Research and Education. Our center is a part of TCG Trust, which is the TCG Center for Education and Research in Science and Technology. And we are actually especially would like to thank Professor Garg for agreeing to give this colloquium, despite being 10.5 hour time difference. Actually, this is nice 7 a.m. in Chicago. So Professor Garg, he obtained his master's from IIT Delhi and PhD from Cornell. His thesis advisor was Professor David Merman. He is best known for Legge-Garg inequality. And this inequality he introduced when he was a postdoctoral fellow with Professor Legge. This inequality, I mean, is used to test macro realism, or also, it is used as a measure of temporal correlation. So actually, this quantum foundation is more of a hobby for Professor Garg. His major interest is in condensed matter physics, in particular in molecular magnetism, and he has done extensive work using coherent state path integration. So in particular, some of his notable works are on effect in investigating effect of friction on electron transfer in biomolecules and topologically quenched tunnel splitting in spin systems. So today he's going to tell us something about how to approach, classical limits basically, because this is you know, a problem, how classical limit approaches for a quantum system. So title of his talk is the classical limit of the spin S Einstein-Podolsky-Rosen-Bohm experiment. So Professor.
Oh, so thank you very much to Professor Pankaj Agarwal and all of you for this very kind invitation to speak and for this very kind, introduction as well. So it's actually a pleasure to be speaking to all of you through this wonder of modern technology. It would be even better if I was, it would be even more of a pleasure if I was there in person in Kolkata and to meet with you face to face. Anyhow, so I think I should begin my talk, and I will share my screen with the video. All right, so let's see if I can make that work. So please tell me if this is working.
Yes, that is it.
Okay, hold on. Let me go to play mode. So here we go. So one of the things that happens when I go to play, oh, there we go. Yeah, all right. So this is the, excuse me for a minute. It's, mm, one of the things that happens is I can't see my cursor. This thing is just. Can the host stop the sharing? Hello? Can you hear me?
Yeah, we can hear you. We are just going to stop this.
Yeah, so what has happened is that on my screen, my cursor is disabled. So there are these things from the Zoom which are hiding the titles, and I can't see my own title. Uh, and I can't get rid of that banner. Uh, it's
We
a
will record
peculiar.
it.
Yeah, if you can stop the sharing as the host, I can restart it later.
So, is it okay now, or is it still
No,
your?
I can't see my own cursor. You know, this is a nuisance because I really want that, and I can't. It won't even let me escape out of the play mode. Uh, no,
Just stop sharing.
this is a issue with the program. With this.
It's okay.
Okay, well, let's just see if we can continue. All right. So once again, thank you very much. And oh, now it has become better. All right. So since I'm speaking to people in Calcutta, okay, now the host has start my video. It doesn't. Okay, I've started the video.
Yes.
Yeah. All right. So is everything running at the moment?
We don't see your slides, but we can see you.
Okay. Let's get rid of that. So. So this is a, well, so we have to view the
Share the slide.
full screen, share, and how's this now?
Now, fine. Yeah, we can see your cursor also.
You can see, well, okay, let me see if I can move this as much to the top as possible. Okay, all right. And now, how's this?
Yeah, much better. Yeah.
Okay, all right, good. So sorry about that little glitch. So once again, it's a pleasure to be speaking to you. And since I am speaking to people in Kolkata, I thought that I would mention that this little point that 2025 is declared as the International Year of Quantum Science and Technology, but this is not actually the centennial of the birth of modern quantum theory. The first paper on modern quantum theory appeared 101 years ago, so more than 100 years ago. And I'm sure you people know what I'm talking about. And this is the paper by Satyendranath Bose on the identity of particles and indistinguishability in relation to photons. And you will see that the date is 1924 on this. And why do I say this is the first paper on modern quantum theory? This is modern quantum theory as opposed to old quantum theory, the old quantum theory of Bohr, Sommerfeld, and all the rules of thumb for semi-classical quantization. So this is modern quantum theory because the concept of quantum statistics and indistinguishability survives intact in addition to Schrodinger's law of motion and the Heisenberg uncertainty principle. Those were formulated in 1925, but the idea of statistics and indistinguishability precedes that by 1 year. So I thought I would remind ourselves of this fact. Anyway, so with that, let me begin my talk. So the title that Pankaj, Professor Agarwal announced is actually too short. What I really wanted was a long title. And here's the title. So it's so long that it takes many slides. So first of all, it's the new and improved, fair, balanced, and optimized, buy one, get one free And then there is a little bit of legal fine print. Approach to the high spin classical limit of the spin as Einstein-Podolsky-Rosen experiment via the incorporation of detector error. So I'm pretty sure I don't have to tell people what the EPRB experiment is. I also had Bohm's name to it because I think his contribution of changing from continuous variables to discrete variables was a big step forward. I was actually very major. In my opinion, I don't think Bell would have been able to formulate his inequality if it had to be done in terms of position and momentum, but because it was turned into a discrete distribution, the mathematical problem became much easier. So anyway, this is the experiment. You all know this. So you have a singlet source of particles. Source that produces two spin 1/2 particles in a singlet state, and they fly towards opposite directions. And there are two detectors, one whose, so there are two Stern-Gerlach magnets. One of them measures the projection of the spin along a direction, which I will denote by A hat. The other one does it along a direction B hat. And in each case, the particle can go into two channels, either m equals 1/2 or m equals minus 1/2. And those two outcomes for particle number 1, I will denote by m1, and for particle number 2 by m2, right? So then the quantity which is measured is the probability distribution. And I will think of this as a distribution for the outcomes, m1 and m2. And A and B, the A hat and B hat are parameters on which this distribution will depend. So if A and B are parallel to one another, you know that you will get perfect anti-correlation. If M1 is plus 1/2, M2 will always be minus 1/2, and vice versa. But if A and B are not parallel, we will get a more difficult, not more difficult, more general distribution. Anyhow, so the experiment consists of doing these measurements for two choices of the axis A and two choices of the axis B. And I will call those A1, A2, and B1, B2. And this is what I will call a 2x2 experiment. And just to set the convention, I will always use hats for unit vectors. That's something that I like. And so every time you see a hat, it will denote a unit vector. Okay. So let's go on. And so now let's do the experiment not with spin 1/2 particles, but with spin j particles. And these are also in a singlet source. And now there are 2j plus 1 outcomes for for each particle. And so now the distribution is bigger, but I denote it in the same way, and it's exactly the same. The idea of the experiment is exactly the same. So this is the spin j version of the experiment, which is the simplest one. All right, so why is this interesting? So let me make sure that this is indeed what I have. Yeah, okay. Now the Bell inequalities, again, I'm sure this is review for most of you. So Einstein, Podolsky, and Rosen in 1935, they came up with this paper on which is based this idea that Einstein is famous for having said. He says that quantum mechanics has spooky actions at a distance. So in German, it's spukhafte Fernwirkungen. And because of that, he said quantum mechanics is incomplete. And so he posits local hidden variable theory, which is that the observed distribution P M1, M2, parameterized with parameters A hat, B hat, is given by this factorizable form. So so I have an integral over lambda and times P lambda, and that is a distribution for some hidden variable. So we imagine that there is some hidden variable, and depending on that hidden variable, there is a conditional distribution for outcome number 1. And similarly, there is a distribution for outcome number 2. And now the key point is that the distribution for outcome number 1 the distribution for M1 conditioned on the value of lambda is independent of what the choice of axis is for the other particle. So P sub A hat is a one axis conditional distribution. All right. And then Bell in 1964 said that, well, so his was the next advance, so nearly 30 years after Einstein, Podolsky, and Rosen. And he said, well, he pointed out that if you look at this, if you take this hidden variable theory seriously, then the following combination of expectation values. So you look at the correlation function of the two spins. So and the 4 is just normalization. If you look at this correlation function, A1B1 plus A1B2 plus A2B1 minus A2B2, that combination, those mean values, that will always be a number which is less than 2. And this is very easy to show. And now this is a standard textbook exercise. So I'm sure I don't have to show it to you. And the subscripts A1, B1, A1, B2, the subscripts on that tell me what the choice of axes is. So I have to do I have to measure these correlation functions for this 2x2 experiment. Okay. So these are the Bell inequalities. And the bombshell is the following. And I want to sort of formulate it like this. Let's put forward 3 propositions. The first one is that there exists a local hidden variables theory. The second one is that Bell's inequality is obeyed. And the third one is that quantum theory is correct. And now it's a fact that if there is a hidden variables theory, then Bell's inequality is obeyed. That is fact number 1. And then it's a fact that if quantum theory is correct, Bell's inequality is violated, it is not obeyed. And so now basic logic says that not B implies not A. And therefore, and since C implies not B, C also implies not A. In other words, if C is true, then there cannot exist a local hidden variables theory. Right? And the experiments done by Aspe et al. And many, many other people since then, they confirm that quantum theory is correct. So we have to accept the conclusion that there cannot be any local hidden variables theory. All right, so this is right. So this is we have now known this for 1964. How much is that? That's almost 60 years, more than 60 years. Well, the experiments are 1981, but there really wasn't any doubt that the experiments would verify that quantum theory was correct. All right, so anyway, so this then raises the following question. So this says that quantum mechanics is incompatible with local hidden variables theory, and how do we understand the classical world? It sort of makes the classical world even more difficult to understand in the light of quantum mechanics. Or maybe you like saying it the other way around, that it makes the conflict between quantum mechanics and the classical world even sharper. Okay, so now you might ask, that's so far so good, what else? Why bother studying higher spin? I mean, spin half already establishes this conclusion. What do you learn by studying higher spin? So let's just, the argument is as follows, that we know the standard commutator for the components of the spin angular momentum. And also then the conclusion that follows from that you cannot know 2 different components of this angular momentum vector precisely. So you cannot know the X and Y component with perfect precision at the same time. And that means you can't assign a definite direction to this operator or this physical quantity to the angular momentum. So just like position momentum have uncertainty, the direction of the angular momentum also has uncertainty. And if I define a new operator, which is a unit vector, by dividing out by the magnitude of the angular momentum, then you can easily see that the commutator for the components of this unit vector is proportional to 1 over j. And as j becomes bigger and bigger, that commutator gets smaller and smaller. And so if two quantities commute, then they are simultaneously measurable. And it looks like if the spin is very large, then the direction of the spin you can assign a classical value or a definite value to the spin, or to the direction of the spin. So this sort of leads to the conclusion that higher spin is more classical, right? So we want to study higher spin in the hope that we will learn something about the connection between classical mechanics and quantum mechanics. All right. So, but then we can derive Bell inequalities for any spin j, and we find very quickly that quantum mechanics violates all these Bell inequalities. So now you can say, well, what happens in the limit as j becomes larger and larger? How is classical physics going to re-emerge? And you can think of two ways in which it might do that. You can say, well, remember the experiment had to be done with two choices of the axis for the measurement axis, A1, A2, and B1, B2. Now, you can imagine that, well, you have to choose this pair, this 2x2 pair of axes very, very carefully as the spin becomes large, and the range of the bad axis choices becomes 0 as the spin becomes large. That is one possibility. But it turns out that that is not true. So this was shown by David Mermin and myself in 1982, that the angular range of bad axis choices absolutely does not diminish as j goes to infinity. It stays as big as ever. And then in 1992, Gisin and Perez showed that the magnitude of violation of the Bell inequalities also does not diminish as j goes to infinity. So that was, you might have thought that is the other possibility, that even though the angular range of violation stays big, the amount by which the inequality is violated becomes small. But that is also not true. Okay, so what this says is that higher spin is not more classical. Okay. So what to do? How do we get classical mechanics from quantum mechanics? How does classical mechanics come out as a limit of quantum mechanics? So are we already there? Yeah, okay. So I want to show you this conclusion to you in a different way. And that's the following. Let's ask about, there's another way to think about quantum mechanical states, and which is in terms of Wigner functions. So Wigner functions are more familiar for position momentum, maybe not so familiar to all of you for spin, but there is a Wigner function for spin also. So let's say I had a single spin particle, then the Wigner function would be a classical function of the orientation. That would give me the probability that the orientation, that n hat, has a certain value. Okay. And then the average value of the x component of the spin would be the classical probability average of n, of the x component of n hat. So that's the second equation over there. And you would write down similar averages for all other operators. But you know this for position momentum, that for most quantum states, in fact, almost any quantum state, the Wigner function is not a positive function. It's not always positive, so it cannot be regarded as a true probability. So the hope that you might have a probability function that gives you the probability for all possible orientations, that hope is not met. So there is no, so sometimes people call it a quasi-probability distribution. And as an example, I give you the Wigner function for a single particle, for a single spin, spin 1, in the m equal to 0 state. And there, if you look at the Wigner function, it has that form which is written down, 1 over 4 pi times that 2.58, etc. And on the right, there's a plot of that Wigner function, and you can see that it's not always positive. It's negative for some values of the range of angles. So there's no true quasi-probability function. So that's, anyway, but this is still an interesting function to investigate. Because, if there was such a classical probability function, if this Wigner function was positive, then you could take the position that, quantum mechanics is just a statistical theory, that for some reason, the things like position, momentum, the spin direction, all these things, anything that you measure, for some reason, there's some uncertainty in it. But but that uncertainty is governed entirely by some classical statistical process. For example, there could be some stochastic process which tells you what the spins are doing in one run and then in different run. Uh, it has some other choice, and and that gives rise to a classical statistical kind of theory of the world. All right, so that's the idea for looking at the Wigner function. And I mentioned this just in order to note that if I have a two-spin system, then the Wigner function becomes a function of two spin orientations, because you have to give it the probability that the first spin is oriented along n1 and the second spin is oriented along n2. So it's just a slightly more elaborate version of the single spin Wigner function. All right, so now for a spin J singlet, what is the Wigner function for a spin J singlet? So this was actually found by G.S. Agrawal in 1993, and then I rediscovered it in 2018. And the equation is given above. And the important thing to note is that, so this is a sum over spherical harmonics. And you might say, but I've seen this before. This is just the completeness relation for spherical harmonics. And the right-hand side is just the delta function. No, but that's not true, because if you look carefully, you will see that the sum on the L quantum number, the magnitude quantum number, L quantum number, does not go to infinity. It only goes up to 2J. And so this is a truncated sum of this product of spherical harmonics. And if you look at this sum, so I've shown this sum over here. I've shown graphs of the sum for various values of J. So on the top left, it shows J equal to 5. And you can see that this Wigner function is sometimes negative, right? X, by the way, the x-axis is the dot product of n1 into minus n2. Okay, so it's minus n1 dot n2. So it takes values from -1 to 1, right? And it's very large when x is 1. So that's just saying that the probability is big when the two spins are anti-parallel to one another, which is what you think for a singlet. But the important point is this is not a positive function. So you say, maybe if I go to bigger J, it will become more positive. So from J equals 5, you go to J equals 9.5, which is the center panel on the top right. And that is also not positive. In fact, you will see that it's more negative than the one for J equals 5. You look at the y-axis scale, and you will see that the oscillations are bigger. They're more, and also the frequency of the oscillations becomes bigger. And if you go to J equals 50, the range of the oscillations becomes so large that if you want to look at the whole function, I have to cut off the scale on the y-axis. And then I blow up the top, the extreme right-hand side of that graph, and you will see that the range of oscillations is clearly bigger than it is for the smaller values of J. And I blow it up even more by a factor of 10. And now you can see how big the oscillations are. Okay. So this also says that higher spin does not appear to be more classical. So we have a dilemma sort of on our hands. Well, not a dilemma, but a little puzzle. And the question is, how do we, if higher spin is not more classical, then how can we get classical limit out of, so, no matter how large we make J, we don't get something which looks nicer. So the question is, how do we get the classical limit for the spin J EPR experiment? And the answer has to be that you have to wash out the oscillations by saying that the detector has some error, that it is not possible to measure any component of the spin with absolute precision. So this is actually this is already a big, a big philosophical leap, because the Heisenberg uncertainty principle only says that pairs of incompatible variables cannot be measured simultaneously with arbitrary precision. But now we are being forced to take a stronger position. We are being forced to say that you cannot measure a single variable, which is now the spin component, Jz, let's say. You cannot measure Jz with absolute precision when you go to, even for large spin, you can't, there is no way in which you can measure with absolute precision. That's the only way in which you can get, in which you can sort of get the classical behavior in the J going to infinity limit. All right, so let's take this position and say that we incorporate detector error, and the particle sometimes goes in the wrong bin. Okay, so shown by those dotted red arrows, it sometimes goes in the wrong bin. And so I introduce an error matrix, RMM prime. And this is the probability, the true spin, which is, so underlying this thing that you measure, there's some true value of the spin, but you observe it in bin, the bin corresponding to spin M prime. And now every bin, the particle has to go in some bin. So, and it, any bin in which you observe, it has to have some true value of the spin. So you find that the sum of this matrix, the sum of any row of this matrix or the sum of any column of this matrix must add up to 1. And then, and for every pair of M and M prime values, all entries of a matrix must be positive. They cannot be negative, right? Because this is a probability that the true spin is being observed in some incorrect, with some incorrect value, right? So then the underlying distribution for my outcomes P M1 M2 becomes sort of averaged, or it becomes coarse grained because of this error. And I'm going to denote that coarse grained distribution with a P bar. I'm going to put a bar on top of it. And so then now the goal is shifted. So the goal now is to find a good R matrix. And okay, so what do I mean by a good R matrix? So first of all, let me give you a totally buddhu R matrix, right? And this R matrix is one where every entry is 1 over 2j plus 1. And this just says that every beam goes into every bin indiscriminately, and all correlations are washed out. There is no correlation at all, and all Bell inequalities are trivially satisfied, right? So obviously, so this is the sort of thing that mathematicians like, right? They say that there exists one R matrix. Of course, it's completely useless, but there exists one. So then the question then is, the real interesting problem becomes, you find a good R matrix that doesn't wash out all the correlations. That just washes out the correlations by just enough. So it is just sufficient. And so back in for my PhD thesis, I found a matrix which was pretty good. It was 99% okay. Okay, it didn't wash out all the correlations, but it washed out. It sort of, it made the probability distribution was still a little bit negative. I couldn't find a good R matrix that. So you have to find one that makes the probability distribution, that averages it enough that the Bell inequalities are not violated, but then doesn't kill all, but just does it by just enough. So it has to be sufficient, and at the same time, it shouldn't be too sufficient. It shouldn't be more than you need. So it has to be sufficient and minimal. So it has these two conflicting requirements that it has to satisfy. And so this problem, I sort of dropped it after my thesis. I was not interested in looking at it anymore. But then a few years ago, I had to think about it again. I had occasion to think about it. And so before I come to that, so that's what I'm going to describe. So up to now is just sort of background. And now I'm going to describe what you might call as the new work. But before I do that, I have to give you a little side tour of a math, some interesting mathematics. So these are, and I want to tell you about these polynomials, which I call the CMMS polynomials. So this is a family of orthogonal polynomials. Okay. So many orthogonal polynomials, Legendre polynomials, Hermite polynomials, etc., etc. This is another family of orthogonal polynomials, but they are not your father's orthogonal polynomials. In fact, they're not even your grandfather's orthogonal polynomials. It turns out that they are your great-grandfather's orthogonal polynomials because they were discovered by Chebyshev in 1864. So they're very old, right? And then they were rediscovered by Meckler in 1958 and then Mermin and Schwartz in 1982. And when they were rediscovered in the 58 and 1982, it turned out that they have connection with the theory of spin rotations, which Chebyshev, of course, was completely unaware of. But so they're actually beautiful polynomials for the study of angular momentum and spin, and they should be more widely known. But so I'm going to tell you a little, some facts about that. So let's look at this matrix, FMM prime, which is the square of the rotation matrix. Okay, so it's the absolute square. And of course, if you don't take that absolute square, that rotation matrix is the Wigner matrix, is the Wigner rotation matrix, is the little d matrix, not the big D matrix. The big D matrix has all three Euler angles. This one only has the middle one. But now we're looking at the absolute square of that rotation matrix, and that's also a matrix, right? And the reason for looking at it is that the probability distribution for this singlet state is actually an element of that matrix, where the angle theta is the angle between the two detector axes. Now, this is a real symmetric matrix of order 2j plus 1. All of its entries are positive. But the fact that all its entries are positive is not the issue over here. Because it is a real symmetric matrix, we are guaranteed that it has 2j plus 1 eigenvectors. And I label the eigenvectors like this. So I put a subscript j. That tells me the size of the matrix that I'm looking at. But now for every matrix, and then there's a subscript L. And the L tells me which eigenvector I am looking at. Okay. And notice L goes from 0 up to 2j. So there are exactly 2j plus 1 eigenvectors also. All right. And the entries of every eigenvector, which you can think of that as a column vector. So the entries of that column vector, I denote by M. So those are labeled by M. And the allowed values of M go from minus j to j. So there are 2j plus 1 entries, as it should be. The column vector size is 2j plus 1. And because it's a real symmetric matrix, all these eigenvectors, they're guaranteed to be a complete orthonormal set. And now come the amazing fact. So fact number 1 is that this eigenvector, if you think about it as a function of a variable m, it is a polynomial in M of degree L. Okay. And the second fact is that it is independent of theta, which is absolutely remarkable. If you think about it as a matrix, and the entries in the matrix, they depend on some parameter theta, then you would think that if I find the eigenvectors of the matrix, they will also depend on that angle theta, but they don't. And the third fact is that the eigenvalue is just the Legendre polynomial P sub L of cosine theta. So this is these are absolutely amazing polynomials. And so you can think about them in many ways. The theory of orthogonal polynomials allows you to do it in many ways. So you can think about it as a set of polynomials on a discrete set of variables, right? On a discrete discrete set of points from minus j to plus j, and you can write it down as an integral with a weight distribution, which is a sum of delta functions at those points. And when you do it that way, the entire theory of orthogonal polynomials can be You can just copy it down word for word. But the polynomials themselves have all these lovely properties. All right. And the reason for looking at these polynomials is that I want to make sure I'm doing this in the right order. Oh, yes, that the measured probability distribution. So if you look at the second line, not the measured, the quantum theoretic probability distribution is just the square matrix. And so you can represent that matrix in terms of these eigenvectors and eigenvalues. You can write it down in terms of a spectral sum. And that is very convenient for analyzing this distribution. So here's the new and improved error matrix that I have found. And the way these polynomials allow me to write it down in terms of that. They allow me to write down this matrix. So you should think of this as a 2 by 2j plus 1 by 2j plus 1 matrix. And you should think of the right-hand side as a spectral representation of this matrix. So it's written in terms of fj of, for the orthogonal polynomial for a variable m and the orthogonal polynomials at the value m prime. And then the coefficient of the two fjlm, fjlm prime, that coefficient is kind of the eigenvalue associated with that matrix, associated with that particular set of vectors. And so this is spectral representation. And now, just to show you that it is positive, I have given you a plot here for j equals 15. And I've given you different sections of this matrix. So I have shown it to you as a function of the discrete variable m for 5 different choices of m prime. And so you can see it has this pretty nice looking structure. It's positive. And as j becomes bigger and bigger, this matrix starts to look like a Gaussian. It starts looking like a Gaussian in the difference m minus m prime. And that's good, right? Because remember what this error matrix is. It says that the true spin m goes in some bin, which is a different value m prime. So let's say I'm looking at spin 21 and m is equal to 5. M prime is equal to 9, then this difference is big, and then the value of the matrix the entry is small. So there's very little probability. Most of the time, if the true spin is m, the measured spin will also be the same value, will be the same number. So in other words, the measurement, the intrinsic detector error becomes smaller and smaller as I go to higher spin, right? Which is good. That's what we sort of want, that we shouldn't need big detector error for large spin. And the width of this Gaussian goes as 1 over the square root of j. So this is the new and improved part of my talk, right, of my title. And then I also claim that it is fair, balanced, and optimized. And what do I mean by that? What I mean is that if you look at the averaged distribution with the detector error included, you can write that in the following way. You can write it as an integral over some unit vector n hat over all orientations of n hat times a p bar for one particle and a p bar for the other particle. And this is exactly like the factorizable distribution that we were trying to find when we were trying to when we started examining the Bell inequalities, right? I don't know, maybe I can go back very quickly and see them and show it to you. This the equation over here that tries to represent the distribution in terms of a integral over some hidden variables like this. So notice this is all of the these are the true p's. The left-hand side is the quantum theoretic distribution. So there are no bars on any of this. The new equation that I'm showing you has bars. Yeah, right. See, it has bars, and this is now the conditional probability that I will measure an outcome m, if this orientation is n hat. And so here's how you want to think about this equation. So n hat is my hidden variable. And the hidden variable is turning out to be a direction. And the probability distribution depends on that hidden variable, the direction. And it depends on the angle between the hidden variable and the choice of my measurement axis. So that let's say that angle is theta sub A. And then this conditional probability distribution is a binomial distribution. So as shown in the second line on the slide. And so it's a binomial, it's always positive, and hence it's a valid local hidden variables distribution. And the hidden variable n, you can think of, if you want to think about it as a, what's the physical meaning of this? You can say, well, this is the mutual axis along which both the spins are actually pointing. That they come out from my source. And really speaking, the spin is pointing along some axis. And you don't know what that axis is. Sometimes it's pointing towards the North Pole, sometimes towards the, it's pointing towards Kolkata, and sometimes towards Evanston. And you don't know what that axis is. And you measure the spin along some different axis. And then the probability that you will get an outcome M is given by this distribution. And now what do I mean by, so this is good. This is a valid factorizable formula, and hence so this is a valid local hidden variables theory. But now I have to argue that this is not a Buddhu error matrix. And by that I mean that I should not wash out the correlations any more than I need. And so what you find is that this conditional distribution actually takes the value 0. It's never negative, but it actually takes the value 0 when you take the axes to be in these special orientations. And so this actually, because it's 0, I say that this is no more positive than you need. And then the other property of this distribution is that it becomes very narrow as J becomes bigger and bigger, and the width in the solid angle becomes proportional to 1 over J. Okay. All right, so now the third claim, that you buy one, you get one free. So the third, and this claim is based on the following kind of argument. So you can ask the following question. You can say this coarse grained distribution that I obtain by taking my, did I write down what PRB is? No. By taking this error matrix and taking my measured or quantum theoretic distribution, averaging it so I get P bar, that distribution, you can ask the following question. Can it arise from some spin state? Is there some state of the spins which will give me that coarse grain distribution? And if the answer is yes, then what is the Wigner function of that state? And you can calculate the Wigner function of this coarse grain state. And it turns out to be the following. It turns out to have this very simple form. So theta is the angle between the two spin orientations, N1 and N2. And it becomes this. And so you will see that so it's proportional to theta by 2. And so that is maximum when theta by 2 is pi by 2. In other words, when theta is pi, when the two spins are exactly anti-parallel, then this coarse grain distribution is very large. And that's what we want. We want, even when so it's positive, but it's really concentrated along anti-parallel orientations. And so the second thing is that this Wigner distribution is always positive. So this is acceptable as a probability distribution. And it also hits 0. It becomes 0 when theta is 0. So it is no more positive than you need. It's also, so this is also fair, balanced, and optimized. And it becomes very narrow as J goes to infinity. And the width in the solid angle becomes proportional to 1 over J. Okay, that's sort of like this fact over here, that the width in solid angle becomes proportional to 1 over J. Okay, so now this is all the math. But now comes the, what does it mean? So this is the fine print, the legal thing that says maybe meaningless. I don't know whether it's meaningful or not. So, but first of all, so first when I found this, I got very excited. I thought it was wonderful that, there's a dual character of this error, that I can think about the error either in this as happening at the stage where I'm preparing the, no, sorry, either at the stage where I'm measuring the spin. So that is where what I started with, right? Detective error. But then it turned out that you can also think about it in terms of the state itself. And and so that is like an error in the preparation of the state. And if this is the, so with this coarse graining, you obtain a probability distribution and you cannot tell where that error is happening. Is it happening in the measurement or is it happening in the state preparation, right? So because it seems like there's this two-faced character to it, it has this ambiguity. And I thought that's a good thing, that there must be something nice over there, that it must mean something deep about this, that I have found some real, wonderful fact about nature, about the classical limit, and this was very exciting. But when I thought more about it, I was not so sure. So I don't know if this is true in India or not, but in the United States, when you submit a proposal to the National Science Foundation, you have to say what the broader impacts of your research are going to be. And here is my statement about the broader impacts of this work. And the statement was made by Mark Twain. He said, "There is something fascinating about science. One gets such wholesale returns of conjecture out of such a trifling investment of fact." So I started out with this, with this very elementary kind of mathematical problem of finding a good error matrix. And then out of it, I came up with this beautiful idea that there is this error where you cannot tell whether it's in the state preparation or in the detection, and this is some fundamental fact about the classical limit. But that's a conjecture, right? So that's my broader impact statement for the National Science Foundation. But it is probably meaningless. And because of the following questions, at least I'm not sure if it's meaningful. Let me put it this way. So the question is, if this coarse graining is intrinsic, what is the mechanism for this coarse graining? Is it the gravitational collapse that DOC and Penrose have proposed, whatever that means, and I say that because I don't actually understand the DOC Penrose collapse proposal. Every time I read it, I'm very confused. I don't understand this. And the third fact is that I would guess that this unknown mechanism agrees with the form that I find only asymptotically as J goes to infinity. And then there's also the question, is the detector error, is it like decoherence due to an environment? Actually, there's one more thing that one should add. I mean, could it also be due to a collapse mechanism like Girardi, Rimini, and Weber? Because that's also the spontaneous collapse mechanism. Is it due to that? We don't know. Can it be described by Feynman-Vernon like influence functional? Again, I don't know. And if it is due to an environment, actually that last point is there's a tantalizing possibility there, that if it's like decoherence because of the environment, then you can have an abrupt transition at some value of J. At least I think it might be possible, because I don't know if you're familiar with this absolutely marvelous work done by Sudeep Chakrabarty in 1981, where he discovered dynamical localization. Actually, Sudeep Chakrabarty and Alan Bray and Moore, they discovered it independently pretty much of each other within a few months of each other. So but if it's due to environment, then maybe there's an abrupt transition at some possible value of J. Anyway, these are my speculations for how this coarse graining might actually be related to some real physics, but all of this is speculation. And now the second NSF criterion, which you have to satisfy when you write a proposal. So first one is, so you have to answer what the broader impact of your research is. And then you have to tell them what the intrinsic merit of your research is. So I have to say that I have no idea what the intrinsic merit is. Okay. It's just an interesting mathematics. At this point, I would just say this is a mathematical experiment which is showing certain results. And just like any experiment, sometimes you see something that you don't understand, but it looks interesting. So that's the state in which I find myself. I have no idea. But if you know, you should publish. Okay, and that's all I have to say. So thank you very much for your attention, and uh, I will stop there. Thanks a lot.
So I mean, thank you very much for this very nice talk. So I think in our audience, if there are any questions, online participant, if they have any question.
So will the questions appear in the chat or?
No, I mean, maybe I think in our audience here, chat also, I think online they may be on chat or they may ask verbally. Is there any?
Okay.
I don't see any questions online. YouTube. Okay, so I mean, okay, let me ask this question. So you were saying this uncertainty, I mean, this error
Mhm.
metric, instead of that, you can think of this as some, state preparation uncertainty, right?
Mhm.
So, I mean, so are you saying then that this limit will work for certain type of states? We have certain states which have that kind of intrinsic preparation uncertainty, then this they're going to infinite limit will be classical. Will be classical
Yes,
limit for those kind of states.
yes, that's correct. So because experimentally what you do is you measure a certain probability distribution, right?
Right. Right.
Now, my position is the following, that you can say, well, maybe the state is not what I think it is, that I prepared the state I tried to prepare a singlet state as best as I can.
Mhm.
But in reality, the state is not a perfect singlet state.
Right.
And the Wigner function of that state, and so you can say, well, what is the state? How to describe the state? So it's not a pure state. So you can write down a density matrix for that state. And that's it's actually not easy to do. But the other way you can describe the state is you can say, can I calculate a Wigner function? Because if I know the Wigner function, that I can calculate every property, every mean value for that state. And the Wigner function is easy to calculate, and the Wigner function is always positive. So if the Wigner function is positive, then you can think about it as a classical state, as there's nothing strange about it,
Mhm.
right? Because
Right.
it's a non-zero, non-negative probability distribution. Sorry, non-negative probability distribution, good probability distribution. Yeah. So that's the other interpretation.
Yeah, yeah, is there any intuition? I mean, like you use this function FLJ, right, to find this error, metric. So was there any
Yes.
intention behind it that why this function worked? I mean, to give you right, metric?
You're asking how I found it.
Yeah, yeah. I mean, was there? I mean, some accidental you tried many different, functions, and so one of them worked, or there was some intuition behind
Well, I don't think intuition is a hard word. So the thing is, when I was doing my thesis, I didn't know about Wigner functions for spin.
it?
And I discovered the business of Wigner functions for spin in the course of doing my work on coherent state path integrals.
Mhm.
Uh, and uh, I actually find it remarkable that G.S. Agarwal knew about these things back in the 1980s. The man knows everything. Uh, and so I was So when I started thinking about it in terms of Wigner functions, there was this other way of trying to understand the quantum mechanical state, and I sort of also I was also looking at the properties of these polynomials for other reasons. Other again, I don't remember now why I was looking again at these polynomials, but any case I was. Yeah. So so you actually were there at this conference in Bangalore
Right.
where
right, right,
So you asked me why I did this work or what the intuition was. There was no intuition, but there
right,
was a need. The people in Bangalore had asked me to give an invited talk,
right,
and I didn't have it. I didn't know. I didn't have anything prepared or anything to say.
right,
So I was sitting in my hotel room 2 days before my talk and just scribbling, and this came out, and so then all of a sudden I had something to speak about.
right. Okay. Okay, accidental. Okay.
So it's, yeah, necessity is the mother of invention, right? As they say.
Yeah, yeah. There was a necessity of talk being in 2 days.
Yes, I had to give a talk, and so that's what led to the work.
Okay.
So
I mean, for this audience, at least maybe you can say just few lines or paragraph about your discovery of, language inequality. And the possibility to say some, I mean, just a bit about history, so how you think that inequality came about, in
oh,
your,
the history is very simple. That
Mhm.
so I did my PhD thesis was on Bell's inequality,
Right.
and Tony Leggett was visiting Cornell,
Mhm.
and he heard me talk about this inequality. And when he heard the talk, he offered me a postdoc. So I was very happy. I said yes, of course. And I went to the to Urbana, and so Leggett, of course, has had a long-standing interest in the foundations of quantum mechanics, and so the idea for developing this inequality was, I would say, is almost entirely due to him. And but I was sort of I knew the technicalities, and so I was able to contribute maybe 5%, and uh, and that's how it happened. So, but
I mean, this idea of looking for macro realism, this
yes,
compromise.
yes, that's correct. That idea is I think so. This is something that Leggett is very much interested in, and this is sort of also. So we did a lot of technical work when I was a postdoc on this business of trying to look at macroscopic quantum phenomena in the presence of a coupling with the environment.
Okay.
Uh, and there's a tremendous amount of technical work that was done. In fact, that paper that I mentioned by Sudhir Chakravarti is in connection with that entire body of work. Actually, Sudeep's paper, I think, is the trigger for a lot of these investigations. I strongly recommend that paper to people in the audience. And if that paper might actually be technical, but there is a review paper by Reviews of Modern Physics by 6 authors. So the
Mhm.
first author is Anthony Leggett, and then Sudeep and I are also co-authors on that. But there are 3 other authors. It's a six-man paper in Reviews of Modern Physics. In one of the sections of that paper, there is a simpler explanation. There's of this discovery of Sudeep's on dynamic localization. Uh, and I really recommend that to everybody in the audience if they have not seen it before. It's a magnificent piece of work. Uh,
Okay.
so yeah, uh, that's sort of the yeah. So we were very motivated in this to try and understand what happens to the quantum mechanics of macroscopic systems. And
Right,
so spin J, large spin J, is sort of like a is in that same class. In that
right, right, right. So yeah, so there is a lifelong interest in testing, macro realism and classical
yeah, that's true.
how to see that.
Yeah, so the but having an interest is one thing, being able to do something interesting is another.
No, that is true. That is true. That is okay. So any other questions which there might be? Okay, so I think we should thank our speaker for getting up so early, at 7 a.m.
I should thank you for staying so late. All right. Well, thank you very much.
So thank you, Dad.
Yeah, bye bye.